Okay, let's start. So we're discussing dynamic programming, and we're looking at this problem called matrix chain multiplication. So you are given a chain or a sort of sequence of matrices A1, A2 up to AN, and we want to multiply all these matrices together, and these are all rectangular matrices. So the number of rows can be different from number of columns, and yeah. And what we know about this matrix product is that it is not commutative. So if you are given, so the order in which you multiply, that really matters. Okay. So if you are given the matrices as A1, A2, AN, you necessarily have to multiply in the same order. You cannot switch two matrices. And it is also associative. Okay, so you can put parentheses at different positions and it will yet give you the same answer. And yeah, so let Mij, this denotes the number of multiplications needed for multiplying AI plus 1 up to Aj. Okay. And we want to use dynamic programming to solve this. We saw the algorithm. Today we will illustrate it using an example. Okay, so we have these two cases. If I equal to j, there is only one matrix. You don't need to multiply anything. So the answer will be 0. And the other case is when obviously j is larger than I. So you need to multiply ai plus 1 up to aj. Okay. And our approach finds some k. So you first multiply the matrices from I to k, then k plus 1 to j. And these two products, you need to multiply them together. Okay. So we are guessing just the last step. At the last step, what are the matrices we have? And for that, the multiplication cost is this much, pi minus 1, pk, pj. Right? Because this matrix, after you multiply from I plus 1 up to k, this will give you a pi minus 1 cross pk size matrix. And this matrix is pk cross pj size matrix. So the total cost will be this much. And this is the way we do our multiplication. Okay, so we are not just interested in the number of multiplications, we also want to know the exact where to put the brackets, right? So we want to actually find the solution, not just optimize the number of multiplications here. Okay, so this is our proposed algorithm, which is you are given this chain of matrices or sequence of matrices in some order. We can't change the order, and let n be whatever is the total number of matrices here, and we have this table for I from 1 to n. Mii is the number of multiplications involved in multiplying just one matrix. So obviously if there is only one matrix, we don't need to do any multiplication. So Mii will set to 0. And there is also this table S, which takes into input two sequences and it just returns an index. So it will tell us where to put that particular bracket. Okay. And we have this. So we want to minimize the number of multiplications. So the standard procedure is there are these two for loops. Okay. For L from 2 to N and I from 1 to N minus L plus 1. Okay. So initially we'll set the number of multiplications to be infinity. And then whenever we find a case such that this quantity mik plus mk plus 1j plus this quantity is less than the current value of mij, we will set that minimum value to mij. Okay. So it's a standard trick. Whenever you want to minimize something, you set it to a very large value. In fact, this could be some large finite value, need not necessarily be infinity. And we keep on updating it till we find the minimum of this expression. Okay. And Sij equal to k, what this means is that the last multiplication that is happening at the kth index. Okay. Because let's say here k was the minimum value for this expression. Actually, k is the minimum index for this expression gets minimized. Then we set Sij equal to k. So that means there is one bracket after the kth matrix and the closing and a starting bracket at the beginning of this kth matrix. And once we return all these M and S, both are bidimensional arrays, okay, two-dimensional arrays, and we return this, so we'll actually get the exact solution, not just the optimum number of multiplication. We'll also know the exact parentheses where they are. Okay. So I hope the algorithm is clear, and let's look at some examples. Okay. So what about this case? Let's say we are given just 4 matrices and we want to multiply all 4 of these together, and we are given their dimensions. For instance, A1 has dimension 5 cross 4, A2 has 4 cross 6, A3 has 6 cross 2, and A4 has 2 cross 7 matrix. Okay, so it is given by a list, the dimensions of all these matrices. And obviously, we want to find the minimum number of multiplications needed to multiply all 4 of these together. Right? So we'll create this 2D array with rows from 1 to 4, columns from 1 to 4. Right? And we'll use our bottom-up approach to compute the number of multiplications for each of these. Finally, we want this value, m of 1, 4. Okay. And we are using bottom-up approach. So we start with the least values. So what we know is m1, 1, 2, 2, 3, 3, and 4, 4. We have only one matrix, so all these values are set to 0. Okay. And then what are we going to do is, here are these remaining entries, right? So we look at the chain length. Okay, how many matrices are there in that particular chain? So we'll update these values m1, 2, m2, 3, and m3, 4. So these are the green entries. Okay. So what are these green entries? So what happens 1, 2? So you want to multiply two matrices together. One has dimension 5 cross 4, the other has 4 cross 6. Right? So what are the total number of multiplications here? 5 multiplied by 4 multiplied by 6. That's exactly 120. And then we want to compute this next one, A2 multiplied by A3. So you have a 4 cross 6 matrix and a 6 cross 2 matrix. and you want to multiply them together. So the total number of multiplication is 4 into 6 into 2. Okay, that's just 48. And finally, you want to multiply 6 into 2 into 7. That's just 84. Okay. So these are our green entries. And now we'll increase the chain length by one more. Right. So that is just this A1, A2, A3. Okay. So let me show what calculations we are making. So this is our M1, 2, and we'll use the same formula. So take the minimum over all k between 1 and 2, M1, k plus Mk plus 1, 2 plus P0, Pk, P2. Okay, so there is only one value possible here, k equal to 1. So M1, 1 is 0. We have already found it out. Similarly, M2, 2 is also 0. This was just find both 6. It's exactly 120. And the same thing you do for M2, 3, M3, 4, and you get these values. And you also store at what value of k this expression is going to be minimized. So here k equal to 1, here it's k equal to 2, and here it's k equal to 3. Okay, so now once we have this, we will move further up. So now we want to multiply three matrices together. So we start with M1, 3. Okay. It's just an application of the same formula. Take the minimum over all k from 1 to 3, and we want to optimize this particular expression. So here it's non-trivial because k could have multiple values. K could be 1, k could be 2. And we just compute both of these expressions and take the minimum over them. So for instance, here we have two things. One takes only 48 plus 40. It's 88 multiplications. The other takes 180. So we are interested in the minimum of these two. So we take 88. And obviously we are splitting, we are taking k equal to 1 here. So we store that value, k equal to 1. Okay, so this value of k will be useful for us to know the exact parenthesization, where we want to put the brackets. Okay, and similarly, you can do for M2, 4, just optimize this expression and you will find that k can take values 2, 3, and 4 here. Okay, we just take the minimum among all of those. So k equal to 3, the expression is optimized. And finally, we'll compute this value M1, 4. So the same expression here, k can take three values, 1, 2, 3. And we just want to find the minimum among all of these. And it turns out that k equal to 3, this expression is minimized, and total number of multiplications is 158. Okay. So the ordering is important here because we are going in a bottom-up fashion. So what we did was we first computed all these entries. So this is the bottommost value, and which was the easiest one. Then we computed in the next diagonal. We got these entries. Then the next diagonal, and finally the last element here. Okay. And yeah, this ordering is usually the most important one, how you will compute the values. And so why we chose this ordering is because once we calculated all these diagonal entries, they don't depend on any of the future entries like this entry. You don't need M1, 2 to compute M2, 2 or 1, right? all of them are just useful for computing the future entries. You don't need to come back and forth. So there are no infinite loops created. It's just straightforward. Okay, so that's the essence of this dynamic programming is that uh, so first you guess a small part of the solution, okay, and you try all possible guesses. For instance, we guessed k equal to whatever values and then took the minimum. So we guess some part of the solution and then try all possible values. And that gives rise to various different subproblems. And we just want to make sure that there is no infinite loop created while evaluating this subproblem. Okay, so it's a fairly simple enough, works for any kind of optimization problem, minimization, maximization. So if you can't think of anything better, of course, uh, divide and conquer and greedy, maybe you can say that they require some kind of intuition about or creativity. But here it's very straightforward rule. You just guess some part of the solution, try all possible guesses, and then look at this subproblems. Okay, it's almost automated. And finally, we'll use this value of k. So we found the minimum value of k where that expression was optimized. Optimization, I mean minimized. Right? And how to compute the parenthesization. So for that, we looked at the value of k where it was minimized and just put two brackets here, multiply from ai to ak and then ak plus 1 to aj. Okay? So there is one bracket here, one bracket here, and then obviously we want to divide both of these things. So again, you will look at the minimum value here. So let's say we have this A1 up to AS1 to N. So S1 to N decides where is the minimum value of K. So we split it into two parts. Now this needs to be split again. So for that we'll use this value. So this part gets split like this. So there is one part from A1 to AS1, S1 comma N, and another part goes like this. Okay, and you keep on repeating this. Again, you'll split in this part, split in this part, and so on. Okay, so we looked at the first S1 comma N values, put brackets A1 to AK plus 1 to AN. Then again, we want to split this. So we use this value S1 comma S1 comma N. So actually, this is somewhat bad notation, but yeah, you can use whatever notation you are comfortable with. So this will be split into A1, A2, AS1, comma S1, comma N, and then the rest will be the remaining half of that. Okay, and this is our print optimal parenthesis. Just here, if I equal to j, there is nothing to do. There are no brackets or anything, so just print blank here. Otherwise, we have an opening bracket, then print the optimal parenthesis for this part, and then put a closing bracket. Okay, so again, we have the same two-dimensional array here. We are storing the value of k, where this particular expression for m1, comma 4 gets minimized. And let's say that was 3. Okay. So for 3, it gets partitioned into S1, comma 3, S4, comma 4. Right? So this means we have A4 separately and there is, needs to be put some bracket for multiplying from A1 to A3, and that we look at this value. Okay, so let me just show you what happens in the first case. S1 comma 3 multiplied by S4 comma 4. So it's just look at the value of S1 comma 3. It's just 1. So it gets split into S1 comma 1, S2 comma 3 multiplied by S4 comma 4. And then we have S2 comma 3 equal to 2. So it gets split into this way. So S1 comma 1, S2 comma 2, S3 comma 3, finally S4 comma 4. So once we have all this, finally you will reach some stage where the first index is same as the second index. And then you just replace it by the corresponding matrix. So this is the parenthesization for that particular matrix. Okay. And you can check that the total number of multiplications involved when this parenthesization is there, and that is just going to be 158. Okay. So any questions with this algorithm which we have? Okay, so there doesn't seem to be any questions so far. And we'll move on to the next problem, which is this longest common subsequence. Okay, so what's this problem? You are given two strings, one of length n, one of length n. So let's say I have these two strings A, B, B, C, D, A, B, A, and B, C, A, A, B. Okay. And you are not allowed to change the order of any of these alphabets. Okay. And what we want is, what is a subsequence in this string is that you can pick any alphabet of your choice, and you're allowed to skip alphabets. Okay. So for instance, you don't pick A, pick B. Don't pick B, pick C. Don't pick D, pick A. And this is one subsequence of this. Okay. Similarly, you can pick subsequence from this Y, or you can pick the entire thing. Absolutely no problem. But you are not allowed to change the ordering of these alphabets anywhere. Okay. And you want to find the longest common subsequence. So what is the longest common subsequence among all these? And so this has applications in various computational biology things, DNA sequencing, and so on. Okay, and it's a very useful problem. Longest common subsequence. So what's the longest common subsequence here? Let's say you pick B, pick C here, then you pick A, and you pick B. Okay, so B, C, A, B. Or there is another one, B, C, A, A. Okay, you pick B, C, A, and A. Okay. And we want to find.
Hello, sir. Can you please repeat what we are calling a subsequence over here?
Sorry?
So can you please repeat what we are calling a subsequence over here?
Yeah, so this is a string you are given, okay, and you are allowed to pick alphabets, okay, and you can skip any alphabets in between and just look at the string which can be formed by picking these alphabets in the same order, okay. So is that clear?
Yes, sir. Yes.
Okay, so this is a sequence of alphabets and you just want to take a subset of this sequence. Okay? So that's called a subsequence. Okay.
And sir, we are allowed to skip alphabets in the second string also.
Yeah, you are allowed to skip alphabets in the second string. But whatever you
Okay.
are picking, that order should be the same as here. Like I can't put some A in the beginning and then followed by B. So the A should always follow B here. Okay.
Yes, sir. Okay, sir.
Okay. So, yeah, fine. So I am given these two strings, x is of length n, y is of length m, and I want to find the longest common subsequence of x and y. And let's say that longest common subsequence has length k. So again, the same thing, I want the optimum value, which is the longest possible such k. And what is that string actually? What is that subsequence? That also I need to know. Okay. So I hope the problem is clear. And in fact, it is approximately equal to the minimum of mn, but it need not be the case. It could be much lower than minimum of. Okay, so this is what the subsequence is A, B, B, A, C, D, C. Okay, so I did not pick A, I picked B, B, A, I skipped C and picked D. So B, B, A, D is a subsequence. The order is same as in the given sequence and they may not be consecutive. Okay, so you are allowed to skip symbols in between. And what do I mean by common subsequence is this thing. Uh, I want the same subsequence in all of both of these. So for instance, what's the longest here? Let's look at one example. One is ACAA. ACAA. Okay. Or you can pick AACAA. Here also you have AACAA. Another option is BACAA. Here also BACAA. Okay, so I hope the problem is clear. We want a common subsequence that is longest, the length is maximum. So this is what a naive algorithm looks like, uh, which is you look at the smallest of the two strings and consider all possible subsequences of that string. So here x is ABACA, y is BCAA. And what are the different possible subsequences of this string? You could have BCA, CAA, or BCAA. Okay. Or you could have just one alphabet BCAA, or you could have two of them, which is BC, BA, CA, and AA. Okay. Or you could have three alphabets, which is BCA, CAA, could have all four. Okay. There is one BAA also. Okay, so how many subsequences you can have for any string? It could be exponentially many. So this is a bad algorithm. that it might potentially take. So there are 2 raised to n subsequences of this thing, and to check whether each of them is a that subsequence also exists here, you will need to check for all m symbols potentially. So the total running time will be m into 2 raised to n. Okay, so obviously this is a bad exponential time algorithm, and obviously we want to improve upon this. And obviously we'll try to use this dynamic programming technique. Okay. Yeah, so I have shown you many examples of how dynamic programming works. So you need to guess something, you need to try all possible guesses, and then look at the subproblems. Yeah, so tell me, what will you guess here, and what is your dynamic programming solution for this? If there is no common character, then answer will be null string. Yeah, that's true. So in general, what's happening here is you are given these 2 strings, x1, x2, xn, y1, y2, yn, and you want to output z1, z2 up to zk such that it is the longest common subsequence of x comma 1. So first we take the simpler problem, which is just output the length of that string, which is k, and then we also want to output the exact subsequence z1, z2, z2. So how are we going to solve this? By dynamic programming. We can divide the two strings into, then we can find the LCS in the two subparts and then merge them to get the final answer. Okay. But is this always going to work? Or, so for instance, I could have probably this works. So you're taking the maximum and then dividing it by 2. Okay, so what his solution is saying is that uh, it's guessing. So you want to obviously divide this into at some point, and then it's guessing the point to be maximum of length of S1, length of S2 divided by 2. Okay. Yeah, this is just one guess which you have. That we guess the middle point to be max of length S1, comma length S2 divided by 2. So in fact, you need to try all such possible guesses. Okay, any other solution apart from this? Can you use our dynamic programming to solve this? Okay, let me pose you an easier question, which is, let's say I'm not interested in finding this entire sequence, Z1, Z2 up to Zk. I'm just interested in the last alphabet, which is Zk. Okay. So can you just find Zk?
Sir, I guess it will be the last alphabet in X that is common to the alphabet in Y.
Yeah. So we need to look at this Xm and Yn, and so there are two different choices here. Either Xm equal to Yn or Xm is not equal to Yn, right? So what's our structure of optimal solution? Okay. So let me tell you that both these last alphabets are equal. Okay. Then what can you say?
Sir, then ZK will be that last alphabet.
Yeah, this A will be the last alphabet, right? Because you can pick the longest common subsequence of each of these and then follow it by A, right? And let's say I ask you, what's the second last alphabet now? That will be just the look at the longest common subsequence of these two strings and find their last alphabet,
Yes, sir,
right?
and we can repeat this process until there's
Yeah,
both strings, one of the strings become empty.
yeah, yeah. Okay. So yeah, divide and conquer. What was suggested absolutely works. We split into the middle and then find the longest common subsequence, but it is not guaranteed to work entirely. Okay, uh, so you need to figure out a very small part of that solution. So here we have looked at the last alphabet and then just keep on repeating it. Okay, so it gives you various sub problems and use those sub problems to find the solution. Okay. So when xm equal to yn, then the last alphabet will be zk equal to xm equal to yn, and then zk minus 1 will be LCS of this. Okay, what about the other situation? Zk is not equal to xm. Let's say these two alphabets are not equal. Then what can you say?
And we will compare x m minus 1 and yn.
Yeah, that's absolutely correct. And or you can compare x and yn minus 1. Okay, either way. Okay. So because ZK now you don't know anything. What is the last alphabet? It could not be equal to this XM, and it could not be equal to YN. Okay. So it falls in one of these categories. And if ZK is not equal to XM, then we have LCS of XM minus 1 and Y. And if ZK is not equal to YN, then we have Z is LCS of X and YN. Okay, let me change the slide. Yeah. And now obviously we want to find this recursively find the optimal solution, which is x equal, we are given these two strings x1, x2 up to xm, y1, y2 up to yn, and let z be the LCS of x and y. Okay. So what are our subproblems here? So we looked at the last symbol, whether it is equal or not. And based on that, we figured out the last alphabet of Z. So there are these two natural problems, which is xi will be just x1, x2 up to xi, and yj will be y1, y2 up to yj. Okay. And Cij will be the optimal length of our LCS for the sequences xi and yj. And now we want to find some recurrence for Cij. So we'll consider two different cases. One is when xi equal to yj, the last symbol is equal. So what will be Cij? This is the length of the longest common subsequence. It is just Ci minus 1, comma j minus 1 plus 1. So the last symbol will always be at the end of this z. So this is one recurrence equation. So LCS of xi and yj is found by LCS of xi minus 1 and yj minus 1, followed by this xm of y. Okay. And what about the other case? Xi not equal to yj. Then we have two possible situations, which is LCS of xi minus 1 and yj, or LCS of xi and yj minus 1. So we have to pick the maximum among these two. Okay. And yeah. And if either of these two are empty strings, let's say, then we know that we'll just output the null string. So Cij will be 0 in that case. Okay. So it will need some practice to get used to this stuff, but I think it is worth it, because then whatever optimization problem you ever encounter in your life, you will always be able to give a dynamic programming solution to it. Okay? So it's a try to use it as much as possible in your algorithms, and think it is worth it. Cij will be 0 if I equal to 0 or j equal to 0, right? It's just a null string here. And Cij will be Ci minus 1, comma j minus 1 plus 1. Okay. If these ij are greater than 0 and xi equal to 1. Okay. Otherwise, it's maximum of these two. If xi not equal to yj. So I hope it is clear what we are trying to do here. And finally, what we want is we want to find the length of the longest common subsequence of x and y. So we want to find C, M, comma, A. Okay, so you are given this x as x1, x2 up to xm, and y is y1, y2 up to yn. And now, okay, so I hope this is fine. How you can find the length of the longest common subsequence? It is just this value of Cmn, and you can find this by bottom-up approach. So you need the initial, you know the initial few cases, C0, 0 is 0, and then we just use these recurrences to find future values. Okay, so this is our algorithm. And now we want to find exactly the longest common subsequence. Okay, so m is the length of x, n is the length of y, and we made this two-dimensional table here. And to find the longest common subsequence, we will need another table here, B1 to M, 1 to M. Okay, so now how will you find the exact subsequence here? So what should this table, what will be the values of this table? So there's a question, is any overlapping subproblem exist here? Yeah. So as we saw here, there's plenty of overlap here actually, because to solve this Cij, you will need this Ci minus 1, j minus 1, I minus 1 comma j, I comma j minus 1. Right? Similarly, when you compute this Ci minus 1 comma j, you will need this solution I minus 1 comma j minus 1. Or even if you want to compute this Cij minus 1, you will need this solution Ci minus 1 comma j minus 1. There are plenty of overlaps, and that's why actually dynamic programming is useful. Okay, let's see this algorithm, which is we know some base cases. Okay, for I from 0 to n, Ci comma 0 is 0, because if this is the empty string, then there is no longest common subsequence. It will just be the empty string, which has value 0. If the first string is an empty string, then you know that again it's the empty string. And then we have this for I from 1 to n, for j from 1 to n. If xi equal to yj, the last symbols are equal, then you have this recurrence relation. Okay. So Cij will be Ci minus 1, j minus 1 plus 1. And let's just, for convenience, because we are going diagonally upwards here. Okay. So in fact, here we are using the top-down approach. If I want to find the value of Cij, I need to compute the value of Ci minus 1, j minus 1. You can use bottom-up approach as well, but yeah, finding the exact ordering, what to compute where, that will require some intuition. So here, just for a change, I am describing how the top-down dynamic programming works. Else if Ci minus 1 comma j, which is the longest subsequence of this thing, is larger than Ci comma j minus 1, then you go on. That will give you the longest one. So there are two different cases. Either you pick I minus 1 comma j or I comma j minus 1. Okay. So what this does mean is that You are going either up or to the left. And we finally return C and as well as P. So what's happening here? Either you go diagonally upwards or to the left. For instance, here you go to the left. So finally, I want to compute this value, okay, which is C7, 6. Okay. So I will just follow these arrows. So here it says to go to the up, then it says go to this diagonal, then go up, then go to this diagonal, then move left, then go to this diagonal, and then go left, and then finally here. Okay. So you understand what we are trying to do here. And it will just show what we really want here. Okay. So whenever you go up or to the left, right, we don't include that symbol, but whenever you go to this diagonal arrow, you pick that symbol. Okay. So for instance, here we went up, so we didn't pick this symbol D. Whenever you are going diagonally, you pick that symbol. Okay. Here we are going up, here we are going diagonally, here we are going diagonally, and so on. Okay. So that's how you will find the longest common subsequence. And it's a very straightforward thing. So this is our solution. Let's say we have this function print LCS. If I equal to 0 or j equal to 0, you can return null. Or if you are going in this diagonal fashion, you call a recursive call to where instead of I have I minus 1, j minus 1, and you print that particular symbol. Okay. Whenever you are going up or this going to the left, then you recursively call this I minus 1 comma j or I comma j minus 1. Okay. So let's say we go back to this example. So here we were going diagonal at these locations B, C, B, A. Okay. And so that's your longest common subsequence. Okay. The remaining alphabets you don't need to pick. So it's almost common sense. Once you can find smallest such thing, outputting the required subsequence is almost straightforward. Okay, but it will need practice to get used to it. But yeah, it's very straightforward. So here we got this BCBA. And what's the total running time? It's big O of mn, right? Because let's look at this pseudocode which we have here. So here you had this for I from 1 to n, from j from 1 to n. We looked at this subcases, and here we are just doing constant amount of work per loop. So this is assuming that we have these values, ignore the recursion here. It's just using some addition, some comparison things, and it's just setting these values. Okay. So in big O of Mn, you can solve this problem. Unlike the previous thing where we take m into 2 raised to n, Mn is obviously much better than that particular bound. Okay, so is there any question?
Sir, why we needed to store the string as arrows? Could not be directly store the string?
Yeah, you can do whatever you want. I'm just showing you I mean, this arrow is just to signify that for I comma j, I need the solution of I minus 1 comma j minus 1. Okay? So you can use whatever symbol you want to use, need not use arrows.
Okay, sir. Okay, sir.
Because you need some way of determining where you are going exactly. Okay? So there will be some programming assignment of this. Where you can use this dynamic programming. In fact, this is a favorite among various, all these programming competitions are there. I think most of them are some dynamic programming thing where you can use it to solve efficiently. So yeah, it's good to have a lot of practice in this stuff. Okay, there is one more question. Can't we use this approach? Make one matrix of M star and put one where the characters of strings are equal, L0, okay, and find the chain of ones which is maximum. Yeah, the same thing. So again, you'll have to describe some procedure to find this chain of ones. Yeah, you don't like these arrows, you can use whatever you want. So it's not a problem. Okay, any more questions on this? Okay, there doesn't seem to be anything, so let's stop this meeting now.